Assalamu alaikum. Today we'll be covering the next portion of the chapter 4.1, which is CPU, Central Processing Unit. And lastly, we discussed our registers, right? So today we'll be moving onwards to system buses, right? Okay, so what are system buses? So these are used to transfer data or addresses or controlling signals, right? They transfer all these. So system buses are used in computers as a parallel transmission component. To learn more about what parallel transmission component, you need to study in depth in the chapter 2 networking, and each wire transmits one bit of data. So now we can see this model, right? So we have our control bus, we have our address bus, we have our data bus, we have CPU, memory, and IO ports. As we can look here, this is a two-way transmission, this is a one-way, this is one way, and this is one way, right? And for data bus, it's always two way, as you can see here, right? So we can figure out that address bus is the only bus which travels in one direction, whereas all the other buses travel in two directions. Like for control bus, you're traveling in two directions, right? So now we move on to their definitions and their functions, right? So the address bus carries addresses throughout the computer system, as you can know by its name. The bus is unidirectional, meaning that it travels in one direction only. And the wider the bus, the more addresses that can be transferred through the address bus, right? So if it is for 8 bits and 8 address, 2 to the power 8 addresses can be transmitted. And if you increase them, you can transfer more addresses, right? So now we move on to the data bus. So the data bus is bidirectional. So bidirectional means allows data to be transferred in both directions. The data bus transfers the data between the components like CPU to IO ports, CPU to memory, and all that. And along as we just read about the address bus, if it is more if it is more wider than more addresses, the wider the bus, the larger the word length that can be transferred. So the word length is basically your data that can be transferred in this sense, right? And lastly, we move on to control bus, right? So the control bus is also bidirectional. It carries signals from the control unit to all the other components, like the controlling signals that we talked about in the first part of this video, right? So this is the bus that takes all those signals to the components, right? And it is usually 8 bits wide, since it only carries control signals. And control signals, like increasing these wouldn't really give you a big benefit, right? Because you only need to control a very limited amount of components in terms of the control bus, right? So you necessarily don't have wider buses for control buses, right? Now we move on to components and their impacts on the computer performance. Like we discussed in the first part about the system clock, right? So the system clock and the control unit work together to control, and the control bus, now that you know about it, they work all together to have this system like feature, right? So that therefore your computer doesn't crash, right? So now the clock speed of a system determines the minimum time interval between processing and execution of consecutive instructions. So meaning one by one instruction. So these decide the speed in which these are performed, right? So by increasing the clock speed and the clock cycles, you are able to process and execute more instructions within the same period. Like if you are performing one instruction per second, now you're able to perform two instructions per second. So you're increasing the clock speed, right? So this is also known as overclocking, as I have indicated right here. And as a result, the processing speed of the system increases. However, we cannot conclude that the overall performance of the system improves solely based on this, because sometimes this causes your computer to crash, because your timing signals are basically in terms of not matching what your component can handle and what your CPU can handle. So this causes a miscommunication between the two, and then it causes computers to crash. If you want to research about this more, there are a lot of videos available on YouTube, and a lot of different and real time examples. Like if you have a gaming PC, like a lot of people overclock their CPUs, overclock their RAM in order to get more performance out of their computers, right? So this is where overclocking works out. Okay, so address and data bus, right? So for address and data bus, we just read that the width of the address bus and the data bus is also important in deciding a computer's performance, right? As a control how many addresses are directly accessible, and how many bits of data can be transmitted at once. So increasing both of these would allow more addresses to be accessible at a single time and more bits of data to be transferred. So if you increase these, you increase your computer's overall performance, right? Okay, so now we move on to the cache memory, right? So the cache memory is also really important in the sense that this is primary memory just like your RAM, but this makes use of SRAM. If you're aware about the differences between SRAM and DRAM, learn more about them in chapter 3. The video for hardware is already up. Okay, so cache memory is similar to RAM in that it stores the currently required data and instructions, right? When a processor reads the memory, it first checks the cache memory and the RAM. So you can conclude that the cache memory is even more important than the RAM in the sense that it is more faster than the RAM. So the computer usually checks the cache and then checks your RAM, right? So the benefit of using cache memory is that it uses SRAM instead of DRAM. That's why used so SRAM is even has a much faster access time and it can improve upon your computer performance because it is much faster and your computer will get fetch the instruction much faster, executed, and then write it to memory in a much faster manner, right? Okay, last we move on to the number of cores, right? So as you are all aware about in your phones and your computers, laptops, we do not use single cores anymore, right? We have shifted to quad cores, octa cores, hexa cores, and all those variations, right? So this is a way in which you can improve your computer's performance because single core processors in the early 2000s were a big thing, right? As you might have known, they were a big thing. But then as we moved on to dual cores, so first of all, we need to understand the limitations of a single core processor. Like during the early 2000s, if you wanted to play a game while running something on the background, a single core processor would struggle, right? So we moved on to dual core, which in its own name allows you to manage things together. So dual cores mean two cores, right? And here we can look upon the definition on what's going on here. So a single core is made up of a CU, which is the control unit, and ALU, which is the arithmetic logic unit, and all of the standards registers that you must have known about when you went through the video one for this chapter, right? However, the increase in performance is not proportional to the increase in number of cores. So this means that if you have a dual core, you're not necessarily doubling the performance. If you have quad core, you're not multiplying the processing power by 4, right? This is because, like, let's read an example here. So doubling the number of cores from 2 to 4 does not mean that the performance will always also double. And this is because we need to consider the different cores now having to communicate with each other as well, which takes time. So in a dual core system, each core only needs to communicate with one another, right? So if you have a dual core, right? So these communicate with one another. But if you have a quad core, you have 6 channels, right? Because these will have to communicate with one another, right? So each has to communicate with 3 other cores, right? So this creates a communication barrier, which turns out to be a limitation, which therefore does not have the performance proportional to the number of cores, right? So this is what it means, right? And this is it for this video. So today we discussed the buses, the different kind of buses, how they are connected, which one's unidirectional, which one's bidirectional, and then we discussed the components and their impacts on a computer's performance, right? So how do these components, if we increase their sizes, if we have more cores, what do they do, what do they limit us to, what do they provide us with? Because at the end of the day, if you're increasing something, there might be a limitation to it. Like if you're increasing the processor cores, then at the end of the day, you're creating more channels, so that therefore it's not proportional. If you're increasing the clock speed, you're overclocking, but it might have a chance of failure, right? So you're increasing your performance, but there's always a cost, right? So you need to be careful about that. Thank you so much for watching this video.